Alright, in this video we're going to be talking about the influence coefficient calculation procedure. The most difficult part of the procedure, and where we're going to be spending the most time on today, is figuring out the geometric parameters that relate the point in space at which you're trying to calculate the influence to the panel. Once you've got those geometric parameters, everything else is just kind of plug and chug, and you can get through it really quick. So let's dive right in. Let's imagine we've got our panel here, and we've got V0, V1, V2. Now remember, we defined that panel 0, or edge 0, starts at vertex 0, and for right now we're just going to concern ourselves with edge 0. These calculations are the same over each panel, so you can just kind of loop through it and repeat the same calculations, summing up the influence as you go. Now, if we've got a point out here, call that point P, the most basic parameters we need to know that relate this point to this panel is the displacements from the point to the vertices. So that's this vector right here, and this is this vector right here. Now, when we define these are always going from the point in space to the panel. And so, if we're going to write out explicitly what these are, we call this R1 because it's tied to vertex 1. This one's R0 because it's tied to vertex 0. And we say R sub I is equal to V sub I, remember we end at the vertex, minus P. Okay? And if all you're doing is the velocity influence calculation, this is all you need. All you need to know is each R sub I and its magnitude. Now you'll notice in the formulas that we deal with R sub I and R sub I plus 1. Again, this is the fact that for edge I, it starts at vertex I and ends at vertex I plus 1. Keep in mind that for this edge right here, we start at vertex 2 and we end at vertex 0. So you can use a modulus to cycle that automatically, or you can just have a special case for when you're dealing with this last edge. That's purely a matter of implementation. Anyway, so again, if you're just doing velocity calculations, this is all you need, but if we're going to do potential calculations, we need to go a few steps further. The next thing we're going to need to calculate is the height above the panel of this point. So if you imagine we draw a line out that's in the plane of the panel, and then we project that point down onto that line, that projection distance, that's going to be h, our height above the panel. Well, if we want to just find h, we can just project p onto our panel normal vector, because we know that that's perpendicular to the panel, and h is the distance perpendicular to the panel. Remember, though, that if we're dealing with transforming coordinates in terms of position, we need to be careful about the origin. So rather than just taking the dot product of p with n, we're going to take the dot product of P with R, and we can pick any one of these R's, but since we're dealing with R, that offset is already taken care of, and we're just projecting the displacement from P to the panel. Now you'll notice, since R here is pointing down towards the panel and n hat is pointing up, if we just say that h is equal to n hat, h is equal to n hat dotted with R0, then in this instance we're going to get a negative h, which doesn't make any sense because we are above the panel. We want a positive h, and so we do h is equal to the negative dot product of n hat and R0. Okay, so that gives us our height above the panel. The next one we're looking at is A, and A is defined as the displacement in the plane of the panel normal to the edge of the panel. Well, if this line that we drew earlier here is perpendicular to the edge of the panel, then this distance here is that perpendicular displacement in the plane of the panel. Makes life really easy. So we can do this again using vectors to project things. A is just the dot product of R sub I, and remember, A is going to be defined for each edge, so we do A sub I. r sub I dotted with, well, what defines that outward normal direction? It's the outward normal vector. Nu hat sub I. Let me clean that up. Oops. Nu hat sub I. So A is kind of odd. It's a little counterintuitive. If P is outside the plane of the panel, then A is going to be negative. But if P is above and inside the plane of the panel, then A is going to be positive. Just something to keep in mind. And a good gut check if you're running through and checking on these calculations. Okay, we've got our radial displacements, we've got our height above the panel, we've got our perpendicular distance in the plane of the panel. There's one more parameter that we can now really easily calculate, and that's called G. If we take the hypotenuse of this triangle that's formed by H and A, we call that G. And using the Pythagorean theorem, G squared is equal to A sub I squared plus H squared. Real quick note here, we're dealing with A sub I because A is different for each edge, but H doesn't have an index because H is going to be constant for the entire panel. It's never going to change. Now, if you'll notice in your influence calculation for the induced potential, you only ever need G squared. So don't ever bother about taking the square root of this. Just leave that as G squared. Store it like that because that's all you're ever going to use. That'll save you some computational time and save you loss of numerical accuracy if you're taking the square root of something and squaring it again. You don't need to do that. Alright, there is one more thing we need to consider, and to do that we need to draw the panel a little differently. Let's take a top-down view of our panel. If we're looking down on our panel like this, our point P is out here. This is V0, this is V1, this is V2, G. We could draw, here are our radial displacements projected down into that plane. R0, R1, we've got A here. The final set of parameters that define this edge are tangential displacements. So we've got perpendicular displacements, now we need to know tangential displacements. So if we project P onto this edge, it's going to sit right there. And so we can say that there's a distance from each one of these vertices. We have L0, and actually I'm not going to call that L0. What this is this is L1 for edge 0. And this is L2 for edge 0. So if you notice in the project description, I call this L1 sub I, L2 sub I. And the way we calculate each one of these is we just have L1 sub I is equal to, now remember what defines our tangential direction. It's that unit tangent vector that we've calculated, t hat 0. So L1 sub I is going to be equal to R0, or in this case Ri, because that's the displacement from the first vertex, dotted with t hat g. Let me clean that up. R1 sub I dotted with t hat I. Okay? And then L2 sub I is equal to Ri plus 1 now, because now we're dealing with the end vertex. Oops. R sub I plus 1 dotted with t hat I. So same direction, but now we're dealing with a different displacement vector. Again, when you get to your final edge, you're going to need to be careful and make sure that you properly handle this I plus 1, because in that case, I plus 1 needs to be 0, because your end vertex is 0. So again, you can handle that using a modulus, or you can just create a special case. Either way works fine. So we've gone over R, we've gone over A, we've gone over G squared, we've gone over H, we've gone over L. Those are the geometric parameters for your influence calculations. Now, let's just take a real quick holistic look at what you're going to do when you're actually calculating influence coefficients. So, if I've got a panel, and again, we're going to sum up influences over each edge. So we've got edge 1, or sorry, edge 0, edge 1, and edge 2. So for edge, we're going to go through a for loop, or we're going to go through a loop, and we're going to calculate all of the parameters for edge 1. So we've got R's, we've got A's, we've got G's, so on and so forth. And we'll calculate all those for edge 1. And then, since we're summing things up, we'll just keep track of these in a variable, or phi, or induced velocity, whichever one you're dealing with. And you can, in Python, you can do the nice plus equals command, and then whatever that function is, that's dependent upon these parameters. Okay. Now, outside of your loop, you need to remember to set phi is equal to 0 initially, and then it can jump into here. And then we'll move on to the next edge. We'll calculate R, we'll calculate A, we'll calculate G, yada yada yada, and that's for edge 1. And then again, go ahead and tack on that influence of that edge based on these parameters, and then you're going to do the same thing for the final edge. So R, A, G, yada yada yada. That's for edge number 2, and then you're going to add that into the influence coefficient phi plus equals yada 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 based on these parameters. And then depending on which calculation you're doing, you're probably going to end up outside of your loop doing phi is equal to phi divided by 4 pi is included in both of these. If you're doing an influence calculation, then you're going to need to multiply by the sine of h. That's all in the formulas that's in your project description. So, just a couple of things to keep in mind. Again, there are certain parameters that need to be recalculated for each edge. There are certain parameters that don't. H is constant for each. H is constant over any given panel. Your R's, so your R's can be reused between panels. So I would recommend going through first and calculating R0, R1, and R2, and then reusing them for each edge. If at each edge you're recalculating R every time, you're going to be wasting a lot of time because you're duplicating calculations. You don't need to do that. But for each edge, you will need to calculate. A and G over again, as well as your L's. There are some C terms in the project description. Those are simply a function of G, H, and R. So those are really easy to calculate for each edge. And that's it. Now you'll need to remember, I guess that's not it. You'll need to remember that when you're calculating these influence coefficients, these are for a unit doublet strength on your panel. Or if you decide to go with the extra credit, these are also for a unit source strength on your panel. So in the formula where it says, phi is equal to mu over 4 pi yada yada yada, leave out the mu. Just say mu is equal to 1. And then when you build up your linear system of equations, that's when you figure out what mu is. Okay, that's it. I hope you enjoyed this and found this helpful, and we'll see you next time.